So section 4.3, we're going to talk about big O notation, and it finds applications in areas such as analyzing the complexity and time requirements of certain algorithms in computer science. So for instance, if you need to figure out how long it'll take to do a sort or a search or different things on large data sets, and there are certain algorithms for it, we want to know how long it will take for those algorithms to run for certain as the amount of data continues to increase in size. And so that's one place it's useful for. We're going to talk about its definition, and we're going to go through how to recognize how different things are written in this notation. So let's start with the definition. It says, let S be a sequence of real numbers. Strictly, sometimes this is also used in function notation as well. And let A be a sequence of positive real numbers. We write S of n is equal to big O of A of n in the case there is some positive constant C such that the absolute value of S of n is less than or equal to C times A of n for all sufficiently large values of n. If this is the case, we say that Sn is big O of An. There's an illustration here of what this represents. You might have two functions that start out kind of one on top and one underneath, but at some point they cross over, they intersect, and one stays above the other. If that's the situation, then the one underneath will never get back up and reach the size of the one that's going up above it. So we usually think of the one that's above it as sort of like the worst case scenario. These could be closer or farther apart depending on how it's constructed. But the one on top, if that one is called A of n, and this one down below, if it's S of n, then we say that S of n is big O of A of n. That's kind of what we visually see here. So a lot of times we figure out where do these cross over, and then we can say from there forward one function is exceeding the size of the other function. And so it's the function for which we have the big O of. Now there's this hierarchy here that they give us here for theorem 1 to show us which are the smaller ones and which are the bigger ones going up the list. So everything below is big O of everything up above it. For instance, since log base 2 is first and the fourth root of n is up above it, log base 2 of n is big O of the fourth root of n, is what they meant to imply with this information. So when we go through a function and to determine if it's big O of something, we're going to use the definition here with this inequality of less than or equal to, and we're going to also write it with that constant there as well. So let's look at a few examples of how we do this. So let's start off with n and 2 to the n minus 1. Now n is going to be less than or equal to 2 to the n minus 1 for n greater than or equal to 3. And to illustrate this fact, let's draw a graph here. This y equals x will be the same thing as our n sequence of sorts, but as a function. We can also graph the function 2 to the n minus 1, which will start off kind of below y equals x, but then curve upward and start growing much quicker than y equals x. And so we can see after we hit the number 3, one function, this function will be the one above, and this other function will be the one below. So visually, that's how we're going to have a big O here for n and 2 to the n minus 1. But however, I'm going to write it like this. N is less than or equal to 2 to the n minus 1, and that's the same thing as 1/2 times 2 to the n power. And the reason why I'm writing it this way is this looks like a constant times 2 to the n. And so since n is less than or equal to 2 to the n multiplied by a constant, we say that n is big O of 2 to the n. Now for our next one, we're going to do n squared and 9/8 2 to the n. So to illustrate how these numbers are changing, let me write a table of some values so we can observe how it's working. Say for n equals 1, 2, 3, and 4, n squared would be 1, 4, 9, and 16. And then 9/8 2 to the n would go 9 over 4, 9 over 2, 9, 18, and it'll just kind of keep going from there. So we can see how at a certain point they're equal to each other, and then after that we expect that one will stay larger than the other. So we're going to say that n squared is less than or equal to 9 over 8 times 2 to the n for n greater than or equal to 3. We could also prove this by induction if we wanted to go into real fine detail about the full proof behind this. But we're just informally looking at it here since we're just looking at these functions as they are. So we see that since that's a constant times 2 to the n, we know that n squared is also big O of 2 to the n. So above we had talked about how n is less than or equal to 2 to the n minus 1 for n greater than or equal to 3. Thus we can say that log base 2 of n is less than or equal to log base 2 of 2 raised to the n minus 1. And by the property of logarithms, this is simply equal to n minus 1. Thus we can see how log base 2 of n is less than or equal to n minus 1, which would be less than or equal to n. So as a result, we can see that log base 2 of n is less than or equal to n, which tells us about how it's big O of n. So we say that log base 2 of n is big O of n. So here we're going to look at the square root of n and n. And if we just jump into a quick sketch of the functions related to these, if we had just, for instance, y equals x, it would look like that. And then we'd have square root function, which looks something like this. And there aren't many places where they're close to each other in value. After a certain point, square root function kind of stays down below, and y equals x keeps on going up above. And it's pretty clear that things like the square root of n would be less than n or equal to n for n greater than or equal to 1. So we can say that the square root of n is big O of n. Side note, we could also go a little bit further with this reasoning and consider another square root function like 2 square root of 3n. Well, we know 2 square root of 3n is less than or equal to 2 square root of 9 times n. And that's the same thing as 6 square root n. And above we were saying, well, that's less than n, and so that would be less than 6n for n greater than or equal to 1. So even in the instance where we have other constants multiplying in here, it's still strictly less than a constant times n. So even 2 times the square root of 3n is big O of n. Now for example 2, it says here, show that for any real number x, if x is greater than 1, then 3x cubed plus 2x plus 7 is less than or equal to 12x cubed. So let's let x be greater than 1, and it's a real number. Since that's the case, then x will be less than x cubed, and 1 will be less than x cubed. And we can verify that, make sure that any numbers are greater than 1. This should hold true. Then as a result, if we multiply both sides by 2 here, we'd have 2x is less than 2x cubed. And if we multiply this other one by 7 on both sides, we'd have 7 less than 7x cubed. Now adding these together, we'd have 2x plus 7 is less than 2x cubed plus 7x cubed. And what I'm going to do here is add a plus 3x cubed and a plus 3x cubed to both of these. So that results in 3x cubed plus 2x plus 7 is less than 12x cubed. And so that's coming from adding the like terms together, the 2, the 7, and now the 3. And so that shows what we wanted to show, that 3x cubed plus 2x plus 7 is strictly less than, or equal to even, 12x cubed. So for these sequences S of n, I would like to go ahead and find their big O relationship. So we'll start off with S of n is equal to 3n squared plus 15n. Now we'll go by the absolute value here, since technically in the definition we were working with absolute value. Absolute value of S of n is equal to the absolute value of 3n squared plus 15n. But since everything is positive here, since n is a number greater than or equal to 0, so we can just strictly say that that's the same as 3n squared plus 15n. But that's less than or equal to 3n squared plus 15n squared. Squaring the n in this case will give us a larger number on that side, and that's equal to 18n squared. Thus we can say that S of n equal to 3n squared plus 15n is less than or equal to 18n squared. And since that's a constant times n squared is the function that this is going to be big O of. S of n equal to 3n squared plus 15n will be big O of n squared. Now in our next example here, we'll start off with the absolute value of S of n. That's equal to the absolute value of 3n squared plus negative 1 to the n times 15n. Now this is going to be less than or equal to the absolute value of 3n squared plus the absolute value of negative 1 times n times 15n. The reason why I'm using this is that we have this property that says the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. And I'm being careful with absolute values here since I do have a negative 1 to the n. So I need to handle those absolute values individually here. Now what this is equal to is 3n, 3n squared, absolute value of it will be just 3n squared. The absolute value of the other term will eliminate the negative 1 and we'll just make it 15n. Okay, and now that's actually less than or equal to 3n squared plus 15n squared, which is equal to 18n squared. So we can say that the absolute value of S of n is less than or equal to 18n squared, and S of n is equal to big O of n squared. So before we go any further, we can actually generalize this big O notation for any polynomial. So if we have a polynomial built up of am times n to the n power plus am minus 1 times n to the m minus 1 plus all the way down to a1 times n plus a0, we have these a numbers as coefficients in the polynomial. If that's the case, then we have that the polynomial S of n is always going to be big O of n raised to the n power. What that means is S of n is big O of n raised to the highest power of n in the polynomial. So anytime we have like n to the second or n to the third, and that's the highest power and it's a polynomial function, then we can know automatically that'll be like n to the third or n to the fourth, whatever the case might be for big O. Also, as a result, we can write the summation k equals 0 of m of ak nk, which is equal to our polynomial expansion up above. We could write that as big A m n to the m plus big O of n to the n minus 1 power. Because basically we can consider polynomial with the terms up to the n minus 1 power as being considered the big O part with the highest power term here in front. Now another notation is called big theta notation. And we say that S of n is big theta of A of n if S of n is big O of A of n and A of n is big O of S of n. That is, S of n is big theta of A of n if and only if there are constants c and d such that c times A of n is less than or equal to the absolute value of S of n, less than or equal to d times A of n. Now what this means is we can figure out a way of placing something below and above a given sequence or function. And that one would then run down the middle between the two. So if we can find a constant so that we have c times A of n and it would go below, and d times A of n and it would go above, and then figure out how to make the absolute value of S of n fit down the middle. And then we have big theta of A of n. And this is useful when we want to try to figure out a worst case and a best case scenario. The worst case would be what's on top, and the best case would be down on what's below. So if we look back from our last example, when we had S of n is equal to 3n squared plus 15n, we saw that 3n squared plus 15n was less than or equal to 18n squared. Now we can continue on here and say that n squared is less than or equal to 3n squared, and that's less than or equal to 3n squared plus 15n, which is equal to the absolute value of 3n squared plus 15n, or, in other words, S of n. So what we can see then is that n squared is less than or equal to the absolute value of 3n squared plus 15n, less than or equal to 18n squared, and that our inequality had also held up above for absolute values as well, so either way we're good. But this is just to show that n squared is less than or equal to the absolute value of S of n, less than or equal to 18n squared. And so we can figure out a way of putting n squared on the bottom side and on the larger side simply by having a constant multiplied by it. So we can say that S of n equal to 3n squared plus 15n is big theta of n squared. Now this next example, it has a lot going on. It says use big O and big theta notation to express these statements. And I'll let you see what those statements entail. But basically what I'd like to highlight here is how on the side here with the 45 absolute value square root of x, we can write that like c constant times the square absolute value square root of x. And then on the other one, that can look like a constant b times the absolute value of the square root of x. So, since this thing here is less than a constant times the absolute value square root of x, we can say that, let's call this f of x for the function. So f of x equals 15 square root x times 2x plus 9 all over x plus 1 as the fact that f of x is equal to big O of the square root of x. Also, we can say that b times the absolute value square root of x is less than or equal to the absolute value of all this stuff here, and that's less than or equal to c times the absolute value of the square root of x. So in this case, since it sits between this one on the low side and this one on the high side, f of x is also big theta of the square root of x. Now in this example, what we're going to do is use the definition to show that 2x to the fourth plus 3x cubed plus 5 is big theta of x to the fourth. Now what this means we need to show is that c, a constant c times x to the fourth, less than or equal to the absolute value of 2x to the fourth plus 3x cubed plus 5 is less than or equal to d times x to the fourth. Now what we can tell here is that x to the fourth is less than or equal to the absolute value of 2x to the fourth if x is sufficiently large. And thus x to the fourth is less than or equal to the absolute value of 2x to the fourth plus additional items like 3x cubed and plus 5. Okay, and we know that this is also less than or equal to the absolute value of 2x to the fourth plus the absolute value of 3x to the third plus the absolute value of 5. And that's less than or equal to 2x to the fourth plus 3x to the fourth plus 5x to the fourth. So thus, as a result of this, we can say x to the fourth is less than or equal to the absolute value of 2x to the fourth plus 3x to the third plus 5 less than or equal to 10x to the fourth. And so as a result, we can say that our function 2x to the fourth plus 3x cubed plus 5 is big theta of x to the fourth. Okay, now for this example, we want to establish the big O for n to the k power for each of these functions. Start out with this one, s of n is equal to 3x cubed minus 1000x minus 200. So the absolute value of s of n is equal to the absolute value of 3n cubed minus 1000n minus 200. And that's going to be less than or equal to the absolute value of each of those, which is equal to 3n cubed plus 1000n plus 200. That's less than or equal to 3n cubed plus 1000n cubed plus 200n cubed, which is the same as 1203n cubed. So what we've shown here is that s of n is less than or equal to a constant times n cubed. So we can say then that s of n is equal to big O of n cubed. Now for our next one here, what I'm going to do first is multiply through by n plus 1 and expand this thing here. If I expand it, I'll get to 2n to the 6th plus 3n cubed minus 2n plus 2n to the 5th plus 3n squared minus 2. Combining like terms, we get 2n to the 6th plus 2n to the 5th plus 3n to the 3rd plus 3n squared minus 2n minus 2. Now the similar reasoning from the last example, we could take the absolute value of s of n equal to the absolute value of everything up above here, and say that that's going to be less than or equal to 2n to the 6th plus 2n to the 6th plus 3n to the 6th plus 3n to the 6th plus 2n to the 6th minus 2n to the 6th, which that would be equal to 14n to the 6th, which demonstrates for us that our s of n is definitely big O of n to the 6th. For the sequence made up of the square root of n cubed plus 1, we can establish the big O of this one by considering the absolute value of s sub n, which would be the absolute value of the square root of n cubed plus 1, which is still just equal to the square root of n cubed plus 1, since the square root is strictly positive. Now what I'll consider is that this is less than or equal to the square root of n cubed plus n cubed for large enough values of n. And thus we can say that this is less than or equal to the square root of 2 n cubed, which would be equal to the square root of 2 times n to the 3/2 power. And so since we can demonstrate that this is equal to a constant, and that's greater than the square root of n cubed plus 1, then we're of the form of constant times n to the 3/2 power. So that tells us that s of n is big O of n to the 3/2 power. Now in this example, we're going to find the numbers such that we have big theta of n to the k for these following functions. So starting with our first one here, s of n is equal to n to the 5th plus 2 times the square root of n. So I'm going to rewrite this as n to the 5th plus 2 times n to the 1/2 power. That would be the same thing as n to the 11 over 2 plus 2n to the 1/2 power. Now we can tell that here if we did n to the 11 over 2 power, then that would be less than or equal to the absolute value of n to the 11 over 2 plus 2n to the 1/2 power. And that would be less than or equal to n to the 11 over 2 plus 2n to the 11 over 2, or 3n to the 11 over 2. So we can see how our function here sits in the middle between n to the 11 over 2 and 3n to the 11 over 2. So we can say that s of n is big theta of n to the 11 over 2 power. Now for our next one here, what I'm going to do first is factor the top. The n to the 4th minus 1, I can factor that into n squared minus 1, n squared plus 1, all over n squared minus 1. That simplifies down to n squared plus 1. So to show by definition here, we know that n squared is less than or equal to the absolute value of n squared plus 1, less than or equal to 2n squared. So we can say that s of n is equal to big theta of n squared. So here we're going to establish the big theta notation for log base 3 of 10 raised to the n minus 3 power. And how I'm going to do this is to start off by considering that log base 3 of 10 raised to the n minus 4 is less than or equal to log base 3 of 10 raised to the n minus 3 less than or equal to log base 3 of 10 raised to the n minus 2. And I'm going to use properties of exponents to rewrite this as log base 3 of 10 raised to the 4 power, 1 over all that, times log base 3 of 10 raised to the n less than or equal to log base 3 of 10 raised to the n minus 3 less than or equal to 1 over log base 3 of 10 raised to the second power times log base 3 of 10 raised to the n power. The function of doing it this way is to show that we have this function here, log base 3 of 10 raised to the n power, and then what's out in front in either case is a constant. The 1 over log base 3 of 10 to the fourth and the 1 over log base 3 of 10 to the second are both constants. So we've established that the thing in the middle sits between a constant on either side times log base 3 of 10 raised to the n power. So that establishes that log base 3 of 10 raised to the n minus 3 power is big theta of log base 3 of 10 raised to the n power. Now for this one here, we have some properties we can use for if we have a n and b n a sequence of positive numbers, then if s of n is big O of a of n and c is a constant, then c times s of n is still just big O of a of n. If s of n is big O of a of n and t of n is big O of a of n, then s plus t, s of n plus t of n, I should say, is big O of a of n. And then this works also if one is big O of a of n and the other is big O of b of n, then the addition of the two is big O of the maximum of a or b of n. And then if you have these two and they're big O a of n, big O b of n, multiplication will also result in multiplication of a of n and b of n. So in the next two examples, I have the big O for each of these, and I'm going to find the big O for the addition and the multiplication. So if you have n squared plus 13n, and you add that with n plus 1 raised to the third, then that would be big O of the maximum of n squared and n cubed. Or in other words, the bigger of the two would be n cubed. So that would be big O of n cubed. For multiplication, n squared plus 13n times n plus 1 to the third is big O of n squared times n cubed, or big O of n to the fifth.